Okay. Everybody ready? Let's begin. Today I just want to show you some tuning issues with MCMCs. Kind of show you how to control convergence. Talk about at least assessing convergence. And so this will help you to understand these issues. This is going to apply to both Gibbs sampler and the Metropolis sampler. Unfortunately, the problem that we're studying is too easy, and so it doesn't exemplify like all the issues. And that again is why I buried the Metropolis sampler in Gibbs, so I can control its convergence and show you issues. On the homework, when you implement your Gibbs sampler and you sample from a normal and you sample from a gamma directly, it's going to converge super quickly. But I do want to show you some toggles and controls, because when you get to harder problems, you'll see these issues. And basically, it's going to mean you need a better proposal, and you have to come up with a proposal strategy. And so all MCMC algorithms differ, for the most part, it's 99% true, either proposal. So I'll remind you that if I use the Metropolis-Hastings algorithm and I use the full conditional, the acceptance probability is 1. So Gibbs is Metropolis. We have symmetric proposals, we have non-symmetric proposals, and they'll all kind of control how well you converge. The closer your proposal matches your target, or can adapt to that target space, the faster it will converge. So with all algorithms, all the issues are all about convergence. So if you want to know all about it, you can build a career on it. So this is an entire field. Okay, so I can't just give you the magic algorithm. And if you've ever studied algorithms in general, there's no magic algorithm. It depends. And so algorithms can do, there's kind of like these two brands of algorithms. Algorithms that are so well tailored to your problem that they work super fast, but they're not adaptable to other problems. And then algorithms that can adapt to lots of problems, like the Metropolis-Hastings algorithm with kind of a general idea of a proposal. It's flexible, but it takes a long time to converge. And so you can have one of those two things. It's kind of like CPU or GPU computing. You can do something fast if it's simple and you have to do it over and over again, but CPUs are more flexible, so you have to give up a lot of time because it manages memory differently. If you understand that metaphor, that's good. It's the same sort of thing. So things can be specialized and fast. So I just want to remind you where we're at with everything. So here's my algorithm, and it converges. And so this is reasonably well tuned. It converges pretty fast, and it moves around the space pretty efficiently. So I have some highlighting in here, and it's showing you the latest samples that are a little bit darker, and then the previous samples are a little bit grayed out. So hopefully what you could see as that thing was running is it was moving around the space fast. It wasn't like stuck in this area for a long time and barely drifted. It's kind of jumping all over this blob real quickly. And so that's what you want an effective strategy, sampling strategy to do. Let me just show you real quickly why breaking things up instead of doing things in block fashion can be effective if you have correlated spaces. So I don't think I explained this super well, but if parameters are highly correlated, and I should say related. When correlated is one sort of relationship, so it's a linear relationship. And we like to discover that relationship. If we can see it, we can understand it, it's simple enough for us to understand, we can exploit it. As things go to the right, things go up, something like that. So we like finding those patterns. Highly related, maybe correlated. You want to update them as block. So probably Probably realistically, block updating in this problem would be a good idea because these parameters aren't super correlated. They do have something to do with each other. This has our n of 200 that we studied last time, and that's why the triangular shape is kind of shrinking away. If you're studying the axes, this elliptical sort of shape that's forming is getting tighter and tighter and tighter too. So as we see more and more data, we see less and less uncertainty. So if I updated it as a GIF sampler, two parameters that were highly related, I'm going to draw them as correlated. So GIFs, so let's say that these are my contours, something like this. So this is my 95% region. Draw a few more contour lines. So this is my contour right here. So this would be pretty correlated. This is like if somebody said, I have all the correlation, and I don't know if you've ever played those games with some app online, can you spot the correlation? You know, you can get kind of good at it. I say that's like 0.92, maybe. So if you update it as a GIF sampler, so GIFs is going to sample from the full conditional from this, and then it's going to sample from the full conditional for that, over and over and over again. So it's going to iterate between those two. So what that means is it can only move in that direction or move in that direction. So let's say we are right here. So let's say that was our point for theta 2. I'm going to update theta 1 first. So it means that I can update in this direction, right here. That's the direction of that full conditional, theta 1. So I can sample anywhere in that direction. Let's say I pick this value, right here. So it's right here. So then I'm going to update the full conditional for this, and it can move in this direction. Let's say I ended up sampling this value right here. So that's in the 95% region. And so then I can sample in that direction. Let's say I pick this value next, and I can sample in that direction. I can do this over and over again, moving in these directions. It's going to take me a long time to get over here. So you're going to be stuck kind of bouncing in here before you can get over here. So you can only move in these axis parallel directions in a GIF sampler. But Metropolis, if I ended up block updating everything, and I kind of was able to learn what the correlation structure is, so MH block updates, same picture, theta 1, theta 2. If I ended up having a well-tuned proposal that kind of knew approximately what this correlation structure was, I could propose, let's say I was here, so I'm considering both values, and I'm going to block update. If I had a well-tuned proposal, it maybe could move in this direction, right here. So if my proposal was something that overlapped this a lot, I could jump from here to here in one step, potentially. And I can move in these directions. So I can move all over the place. Where GIFs is constrained to move axis parallel. So that's the reason that a Metropolis sampler, even if you have a low acceptance rate, can converge faster. So it's sticking around the mass. It's trying not to jump out here. And so that's sometimes why you would want to break things apart. What do you do in general? Well, it depends. You know, what's your model? Sometimes we know things about how the parameters are related, and that you'll get through experience. So you'll play around with hard problems. If this sort of strategy that we're developing with the symmetric proposal or a truncated proposal doesn't work for you, you'll need a different proposal, i.e. you'll need a different Metropolis algorithm. So, i.e. you'll need a different MCMC approach. So some people develop that for a career. So Bayesians build these models, likelihood times priors. They like MCMC because it allows them to sample complicated posterior distributions. MCMC is not Bayesian, but Bayesians use it as a tool. So a modern day Bayesian, you'd be hard pressed to find a Bayesian that doesn't know a lot about MCMC samplers, or something like it. There's other approaches. There's filtering techniques, particle filters, and there's kind of these different brands of which computational approach do you use. Okay, so this one's very popular. Jen?
So my question has to do with the decision step of the language.
Okay.
So when you're doing the block sample, right, you realize that the alpha is chosen from the minimum on the front.
Yes.
There is the ratio of targets, and I suppose for block sampling, that is going to be the Bayesian statistics.
That's right. So if you're block updating, you're updating both parameters at once. So in the context of our normal example, you would propose both a phi and a mu. So phi star, mu star, that would go into the numerator of that ratio. So let me just write it down since this is the second time somebody's asked about it. So block updates. Here's the decision rule. So you're going to have a mu star, phi star. I'll write it down in the case of our example. So you're going to have minimum 1 pi mu star, phi star given x. So this is what you're going to be doing on your homework. Mu t minus 1, phi t minus 1, given x. Keep in mind, this is just likelihood times prior. You don't need to normalize it. That's one of the beauties. If you could normalize it, you could build a better sampler probably. G, this is going to be mu star, phi star. If you were building it in a Markovian fashion, is all the articles that I give you suggest doing. This would be the inverse proposal. So you're just updating both things together. So you propose them together. What is this right here? If you propose them separately, like this code does, you can take those two things, and this would just be the product of your two proposal densities. So for the symmetric proposal, everything would cancel. You'd be left with, if you use the truncated strategy, this ratio of those CDFs.
So my problem with this is, in our homework assignment, right, we are looking to sample from this joint distribution in the first place. So why is it necessary to go through all of this when this itself is the question?
You don't know how to sample from mu and phi.
When we're doing that, right?
Yes. So what do you mean? Why do we have to go through it? We have to go through it if we're going to do this stuff. So what else do you propose?
So my thought was that we are trying to sample from this joint distribution.
Yes.
And we are claiming we don't want to do that.
That's right.
So how is it that we are getting these values, which themselves are coming from the actual distribution?
No, they're coming from G. So mu star, so I'm going to end up taking mu star. It's going to come from G, mu, given mu t minus 1. And I'm going to take a phi star, and I'm going to grab it from its G. These are different G functions. Okay, so mu, phi. They live in different spaces. Phi given phi t minus 1. So maybe this is the symmetric proposal. Maybe this is the truncated one. So this thing right here, so I'm able to sample these. I still can't sample from pi, and I don't know how to do it. I really don't. So even though a lot of this seems like a fiction, that one joint distribution, you really don't know how to sample from. So you come up with something. This is like a symmetric normal. That's certainly not the target. This might be a truncated normal. That's certainly not the target. And these proposals are able to walk in space. So walk up and down the tails of everything because they move because they're Markovian. All we're doing in this step is evaluating the function. I'm not sampling from it. Yeah, sometimes, I don't know what it is, but Jenny, you're not alone. Year after year after year, evaluating a function and sampling from it are entirely different things. Click. Okay. So this right here, just finish up. This is just going to be the product of G mu star given mu t minus 1 times G v star vt minus 1, because we proposed them independently. So you just product those things together. If this was the symmetric proposal right here, they'd be canceling in the ratio. You wouldn't even write it down in your decision. Okay, so we're all on the same page. So, oh, Danielle, please.
So for the gigs, we said that we are sampling from the full conditional for like each marginal. And so what do we say we're sampling from for the block? Is it the joint?
Yeah, we're sampling the joint.
Okay.
Exactly. So if you iteratively, and in my code I'm doing both. I'm sampling from the full conditionals but using Metropolis Hastings step just so I can show you tuning issues. So you wouldn't actually do this in reality. You'll see that on your homework. For this problem, just sampling the full conditionals is good. But I like you to see issues up front, because you will encounter them. If you're an MCMC person, you're going to see these issues all the time. Okay, so I have a couple toggles in here. I haven't said anything about my step sizes that I need to use. So this is kind of like a Goldilocks thing. You want your step sizes to be just about right. You know, you don't want to overshoot the target, and you don't want to tippy-toe through the target. So this is what an MCMCer does, is they start out with some sort of a, let's just see, this is why I ended up doing this step size. I'm going to make this really small. So this has to do with my proposal variance right here. You can play around with this in the code that I put online. So I'm going to just make it really, really small. I'm going to make it really tiny. Save that. Let me just show you where it comes in this code. So when I propose from a random normal 0, 1, and I multiply by something. And why did I divide by 10? I just did it. You know, there's no reason. So I was just playing around. That's probably in that part of the code the last time I taught this. So that's the way it runs. So, but this is controlling the variance. I'm centering it where I was last time. In this step right here, while there's a small mistake, I'd like you to correct it in your homework. I think I did say send me in an email in the code that I uploaded. That was for a previous year, so just put it in your homework, how you tuned it. Tell me what your proposal was. It's all in that web blog from Darren Wilkinson, so it has the answer to that. Saying that if you didn't do it, you already know I can't tell. You know, I'd have to like give me all your samples and do like a test or something to see if, you know, you are in. Really can't tell. So same thing down here, I have some step size. These converge at different rates, and that's why I multiplied by different numbers here. So phi converges at a different rate than mu, so that's why I multiplied by a different number here. Same sort of thing I'm sampling from a truncated proposal. It's not symmetric, so you do need that correction factor. I put everything on a log scale, not meaning I've taken the likelihood times prior and then put that into a log function. I algebraically figured out the log, and that's what I coded up. And I have everything done on a logarithmic scale. So that's just to make everything numerically stable. If I don't do that, it never converges because I get numerical inaccuracies. Okay, so I've made that proposal now really small. I'm going to start it at exactly the same place, and we'll see what happens. So this is the same thing. So we kind of see the convergence pattern is quite a bit different here. So remember, it just shot down real quickly and boom. This is converging very slowly. And hopefully you can see where the samples are. They're kind of tiptoeing around the space. So my proposal is like just kind of barely budging around the space, and it's trying to walk up this tail. So if you have super small step sizes, it won't converge very fast. You won't burn in very fast. Now you could still deal with that, but you're going to have other repercussions. So maybe we speed it up a little bit. Maybe we make this thing really, really big. Oh, and let's just look at these trace plots right here. This one right here, you're maybe thinking maybe it's converged after a while, and maybe that is convergence. And that's for phi. This one's for mu, right here. And so there's obviously it hasn't converged to some distribution. You know, it's supposed to be in that distribution and stay there. So it's still snaking around. So this is what I call snaking. A trace plot that snakes, and most people will use that terminology. So if it's snaking, what do? You crank up its proposal step. So you make it bigger. So snaking looks like this. So it's stepping too slowly through the space. Your acceptance rate goes way up when you do this. So because you're always proposing right next to where you were before. And so if we monitor our acceptance rate, it would be high. And if I made that number, the proposal variance really, really tiny, my acceptance rate would go really high. And we could monitor that, and I suggest you monitor that in your code. So a high acceptance rate does not mean a good thing, necessarily. It's like, okay, you're storing less samples, but you're converging really slowly. Let's get this closer. Let's at least say, well, we kind of know where the truth is. So even if I got through burn-in, this snaking sort of behavior isn't great. So what I'm going to do is I'm going to take something that we know where this thing, where the truth is. So I'm going to at least get us through the burn-in period. I could run this for a long time and get you there, but we'd burn up too much of the class time doing that. So I'll let you play around with some of this, but I'm going to say, let's just start this closer to the truth. How close? Real close. So I should have just made it the truth or something like that, but we'll just make it that. So we're going to be through burn-in. So if it hasn't burned in, you can't report anything. Those samples are junk. I'll just run this thing again. So I was close to the stationary target. You can see the truth in there. That's the red dot. And this thing is moving through this space, and we already know what the converged distribution looks like. It's going really slowly through that space. So even though we're kind of in the posterior mass, we're still not effectively learning what those contours look like, because it's not able to move through it fast enough. It's barely walking through this joint space, and we can kind of see that in these trace plots right here. So these are like the last 1,000 samples. They're all collected over here, so it's not effectively able to move around this thing. So even though you've honed in on the posterior mass, you haven't learned the tail behavior of this distribution. So that's not converged. And you can easily detect that by looking at this trace plot. So sometimes when people come in with really lousy looking trace plots, they're like, oh, they're always kind of in this range right here. I'll say there's some semblance of convergence there, but it's not very good. Now, one strategy people will have for highly correlated chains where it's snaking around and they can't come up with a better proposal strategy is they'll thin their chains. There's no theoretical reason to do this. What that means is instead of storing every sample, you might store every 100th sample, so that at least you store less stuff. So if I uniformly sample from a sample, it's still a sample. And so that's effectively uniformly sampling from a sample, even though I have a systematic rule that every 100th sample, thinning will only save you with storage problems. So you can do that. It still takes a long time to run the chain, so I'm not going to say too much about that. So it's nothing theoretical, it's just kind of a practical thing. You can throw away samples if you want, just so you don't have to store like a 5 terabyte file of all these stuff waiting for it to converge. This is a clear symbol that the thing hasn't converged. It's not converging well. So what do you do if you're doing Metropolis Hastings? You become a little bit more ambitious in that step size. And so you crank that thing up. Let's crank it up really high. Now I know I'm controlling both of them the same with this one toggle. It's okay for these purposes, but you can tune each one of those proposals separately of each other. We probably should tune the mu one, but I'm going to just tune them both. And I'm going to say my step size is much more ambitious. My variance is big. So let's go the other way. So this is kind of the Goldilocks phenomenon. We go too extreme in one direction, we go too extreme in the other direction, and we get an idea of what might just be the sweet spot. So we just kind of iterate. And this is what MCMCers are doing in their office all the time. Is they're playing around with things, tinkering, and then looking at trace plots. At the end of the day, we might report something more sophisticated, but usually you're visually diagnosing this thing. So I'll run it again. So this is a little bit different, and you can see this axis parallel sort of behavior because I have it in the Gibbs sampler. So this does plot everything, both samples at a time. What's happening right here is one of those parameters is probably not updated very often. So every once in a while it does kind of cross the diagonal. And that's just a phenomenon of my plotting. So we can look at these trace plots right here. It's not that bad. This thing's kind of looking okay, but if you brought this to me, I'd say run the thing longer or get a better proposal. You see these stripes that it's hard for it to land in here with this huge proposal. Jumping all over the place. Why did it miss this ribbon? I think it's coincidence. But you can see this phenomena by looking at this trace plot right here, so it's sticking. So trace plots that do this are said to be sticking. Where your trace plot looks like this. So it's rejecting a lot. It's not accepting a move. It's just stuck somewhere. And the reason why is your proposal's throwing it way outside of the target. We have to wait until our proposal gives us something reasonable. So, and that's that phenomena. So what do? You don't report the answers yet. We can kind of see that this isn't the right answer on feed. Gamuts don't look like this. This is too clunky. So that's not a very refined histogram. Mu looks all right, but if I saw this, I would think, well, probably, there is an interdependence between these parameters right here. I probably just need to work on this for a while until it converges well. Then we come up with something reasonable. So after we do this, I take that step size and I make it something a little bit more reasonable. It will depend on your target. So as n gets bigger and bigger and bigger, my target's getting tighter and tighter and tighter. So depending on n and the data that you observe, you'll have to retune your algorithm. And you might know how to do that. You might have theoretical reasons, for n this, I scale my variances to that, but I would say that's all experience. So, Stephen?
So you said with snaking your acceptance rate is super high, and then with this it's really low, right?
Yeah, that's right.
So is there once you converge, is there a good acceptance rate?
Let me say something about that in a second. So you can play around with this. I'll say this. For normal sampling, now this is a total fiction. So if I'm trying to sample from a normal distribution, and I have a normal random walk, it's trying to sample from it, and that's where all the theory comes from. So if you could even sample from a normal random walk, you'd know how to sample from a normal distribution. So you never do that. But there is some theory that says, what's the best acceptance rate if you were to do that? If you had something that was regular, well-behaved, didn't have modes in it, wasn't super skewed, didn't have heavy tails, didn't have a witch's hat, so that's where things get tighter and tighter and tighter as you converge in on the point, and it's hard to get everything right in there. So if you had a nice smooth problem like a normal distribution or something close, and you're using this normal random walk strategy, 38% is the number. It's true. And theoreticians will go through it. I've watched this a couple times in my life. People prove that. It's in some of the hardcore MCMC books, the more theoretical ones. That is such a rough rule of thumb that I don't use it for anything. So you don't want it too high, you don't want it too low. 38% is kind of an optimal answer on an easy problem. And when people ask me that, they're like, what's your acceptance rate? And it's like, 15%. Oh, shouldn't it be 38? I usually laugh, I don't know. This is a really weird problem. What is the optimal acceptance rate? So I don't know the answer. So what you're going to do is you're going to look at these trace plots. What you really want to do is make sure you can mix fast. So there is theory that says this is the Markov chain that you're forming. There's theory on controlling the flow of a Markov chain. So in a Markov chain, you want to be able to move fast, jump state to state, get from the most extreme states to the most extreme states. So there's kind of a confluence, this flow in the Markov chain. That flow rate for an algorithm is controlled by, get this, not the first eigenvector, the eigenvalue for the Markov chain. So you have this matrix, we know about linear algebra, we can look at its eigensystem. It turns out in a Markov chain, the eigenvalues are always bounded by 1. So, always. So the norm of them is always bounded by 1. That's because everything adds up to 1 in the Markov chain, because it's a probability space. We're integrating in a continuous space. The distance of the second eigenvalue to the first eigenvalue, which is 1, there's always an eigenvalue of 1 in a Markov chain. If you don't know that, take a stochastic process class, it's cool theory. That distance is called the spectral gap. And what you basically want to do is make that big. And so algorithms with bigger spectral gaps tend to be better. And that bounds the mixing rate. You have to learn a lot of theory to know this. We're not going to do it here. So there is theory. The hard part is in most complex algorithms, you can't work out the eigensystem. So you would never be able to do it. So because the proposal's so complex. So there is theory, but most of the time you're like glancing at these trace plots and seeing that they are not snaking and they're not sticking. I say they should look like fuzzy caterpillars. So that's not a technical term. So if you use that, cite me. So, I have a story about that. I have an affinity for caterpillars, but I see caterpillars. So anyway, those are basically the principles, and that's how far we're going to go into it. I will teach you about detailed balance next week after the midterm. If I teach it to you now and ask you about it on the midterm. I'd rather teach you what Jeffrey's priors are and start on that next time. So I'm going to ask you about Jeffrey's priors on the midterm. So if you want to glance at that, that's good. It's really just a calculation, so that's easy. So before I do that, I want to tell you about this rat problem. If you've had time to watch the review session, I talk about it at length. I talk about it at more length than I'm going to talk about it now. So if you want a little bit more of a lesson on that, read the Gelfand and Smith paper that's online. So I'm asking you to code up the Gibbs sampler, not code it up, just describe it, write down the full conditionals. Later on, I'm going to ask you to code this thing up. Later on, I'll teach you about the detailed balance proof and how it proves that the Metropolis algorithm converges to the right thing. We'll iterate. So right now, let me just describe what the Gelfand and Smith paper, this one that they've done before they wrote the big Gibbs sampler paper. So they followed that paper up in 1990 with a publication that I'll share with you soon. It's much more technical. It says theoretically why that Gibbs sampler converges. Right now, we just have a engineering understanding of it. It seems to work. We kind of know how to play around with it, which will be sufficient for this homework. So this is the rat problem. And this is the problem that Gelfand and Smith used to motivate Gibbs sampling. So here's what the problem looks like. You end up observing rat weights. So this is going to be the weight of the ith rat at time t. So they're going to motivate this a little bit more in the paper while they're studying rat weights. So the biologists will tell you all about that if you're interested. But you guys know the scenario. They do something to rats. They watch them over time. They compare them to So they might be testing out some pharmaceutical thing. Maybe they're looking at, let's imagine they're looking at protein shakes and they want to figure out what's the best protein shake to make these rats put on weight. Or maybe it's a diet pill. Who knows what they're doing to these rats, but they're watching them, they're seeing how they evolve over time. So they want to study this. So the model that they ended up invoking for this is very 1989. So it's not probably what people would do today. But here's their model. They end up saying that there's an intercept and a slope. So intercept, and this is going to be a slope. So it's a linear model. They want to understand the linear trends as everything evolves through time. So this is going to be a time increment. They're extremely fortunate that they're able to measure these rats over and over and over again for all of the time elements. So this is going to go from 1 to cap t right here, and they're equally spaced. This is really convenient. You know, I never see data like this. So usually it's like intermittent, not on the same intervals. You got to do all these statistical things. So the ith rat, they're going to end up observing I different rats. I goes from 1 to cap I. So this is the number of rats. This is the number of time points. So they want to see basically if the rats are putting on weight in a positive manner, they're growing or they're shrinking. But they want to do this for each rat individually. And I go into a big explanation about random effects, but this is an effect that's random to each rat. So each rat has its own set of coefficients. We're able to learn about each rat because we get to observe something through time. So we have these repeated measurements through time. And there's going to be some sort of error right here. This is error t. And error t, they're going to do nothing fancy. They're going to make that normal 0 sigma squared. And I'll call that 1 over phi. So we'll do inference on phi. So it looks pretty simple. There's a little bit of a hook right here that there's a relationship between all the rats, that there's some sort of a population mean on these parameters, and they want to understand if these parameters have sort of a relationship to them. So the extension to this model is called a random effect. Each rat has a slightly different effect, propensity to put on weight or to reduce their weight over time. It looks like this. Alpha I, beta I. These are going to be normally distributed. So there's some sort of a population mean. So I'm going to call this alpha 0, beta 0. That's where the population of rat parameters are centered. So they're doing this very statistical thing. They're kind of morphing the biological relationships of the rats into these parameters. I.e., how heavy was the rat when it came into the study? So if t is equal to, and let me change this. Let me make this 0. So that at time 0, this is the rat weight. That's kind of the initial. And this is its propensity to put on weight through time. So if this is a positive coefficient, then they're going to be increasing weight over time. If it's negative, they're taking off weight through time. Here's the population mean of rat parameters. So in this kind of statistical lens, this simplified model, what they're really interested in is this covariance matrix right here. And so this covariance matrix, oftentimes I invert it, and I'll talk about the precision. I'd like to talk about this a little bit in more detail. So this is covariance. And sigma inverse is known as the precision matrix. I typed up an excerpt for you and I put it online as to the interpretation of the coefficients or the values inside a precision matrix. The key point is that the zeros in this matrix mean something very important about conditional dependencies. You can read through that. It's 2 pages. So, and I just showed you the normal theory. So if you're acquainted with normal theory, in regression models, the elements of the inverse of the covariance matrix are the partial correlations, if you're familiar with that. If you've ever taken a Stat 101 regression class, they would have talked about those. Anyway, lots of important stuff. I usually like to study this matrix and not necessarily that one. So I'll give you just a little bit more of a precursor. If you have a diagonal precision matrix, it means each element is conditionally independent of everything else. That's obvious. If you have a tridiagonal, it means that you have a Markovian structure. So it means that every element is only conditionally dependent on its neighbor. And all the other elements will be zeros. It'll tell you where those conditional independencies are. I wrote that down for you in this 2-page write-up so you can read through that. So this is going to be I goes from 1 to I. So the idea is this, that we're going to reach into this collection of rat parameters. Each rat is going to get some set. So that's its genetic ability to put on weight. And those are what this parameter is. This is about how heavy it is coming into the study. So each rat gets selected, and then they end up producing this time series of weights. Boom, 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 boom. And so this thing right here is going to be some matrix. I'll call this variance alpha. I'll call this variance beta, and this is the covariance. And the big question right here is this a zero? So what is that value? And they want to know what that is. They want to learn that relationship. So the big scientific question is the rat's propensity to put on weight or take off weight related to how heavy it is coming into the study? That's what they want to know. And there's good reason to think both things. Has nothing to do with anything. So I don't know, I always think that there's a relationship there. So if you know, and we see it in the gym all the time. You know, maybe people that are a little bit bigger are able to put on mass faster. I don't know, possibly. So you could go the other way around. And I've heard this argued both ways. You can look at the paper and see what it is for these rats under this condition, this treatment that they're giving them. But maybe people that show up to the gym and they're bigger are able to take off weight faster. Maybe they're able to move their weight faster. I'm not sure. So it kind of depends. And I bet there's a lot of variation in this. So, but they want to learn that, and that's going to be identified through this parameter. So the idea is to work out the full conditional for all these parameters that you don't know. So I'm going to call this theta I. I'm going to call this theta 0, just to give myself some notation. And we're going to be able to write down the likelihood function for everything. And so the likelihood model for this, and I'll just point out this thing has some model. I'm going to call it FWIT, given its parameters. I'm going to call those theta I. That's these. I'm going to say we get the time periods, so I'm not going to write that down in any glorified manner. There's no x's here except for time. I'll just indicate that I happen to know that. And then there's this other parameter phi right here that everything is conditional on. And for this model right here, I have something else. I'm just going to pick a letter. Pi is what I'm going to call it. Kind of looks like a posterior distribution, but it's actually a random effect distribution. So if you don't get that, you want to call it a prior, I don't really care. That's fine for me. If you go into this statistical community, they'll yell at you for doing that. They'll say, no, it's not a prior distribution. Computationally, you handle it as such. You run a Gibbs sampler on this whole thing. But it's part of the model. I don't really care what you call the model. Most people call the likelihood function the model. I call the likelihood function and the priors the model. So it's just a matter of semantics. But this is called a random effect distribution. This is a distribution on theta I given theta naught, those parameters, and sigma. And so I can write down the entire likelihood with this notation. It's going to look like this. And I should probably tell you what these things are, just so you can work through everything. This thing right here, this is a multivariate normal. It looks like this. This is going to be proportional to sigma minus 1/2. That's the covariance matrix. There would be a 1 over 2 pi raised to the second power because this is two-dimensional. And I can write this down is equal 1 over 2 pi square root squared, because that's the dimensionality of the problem. This is e to the minus 1/2. This will be theta I minus theta naught transpose sigma inverse theta I minus theta naught. So that's a multivariate normal. This thing right here is a one-dimensional normal. So this just looks like 1 over square root 2 pi. This is going to have my variance term. I'm writing it in terms of precision. So v to the 1/2, e to the minus 1/2. Give myself a little bit of room. WIT minus whatever its mean is. I'm going to write this out in matrix notation. So this thing, I'm going to write it like this. Theta I transpose times 1t. This is a matrix. This is a vector. This is a vector. When I multiply them together, you get that. So it's a dot product. So this is a vector going in this direction. This is a vector going in this direction. This is alpha I, beta I. This is 1t. Good. So it'll make our life a little bit easier to write it out like this. Theta I transpose 1t squared, and there's a phi right here. So the likelihood, and I'll let you think about this and we'll pick up with this next time before I jump into Jeffrey's priors, is the likelihood is going to be the product of the number of things that happen. So for each rat, they get their parameter set out of this. So boom. So for each rat, you get this. Pi theta I, given theta naught sigma. So each rat gets its parameter, and then we get to see its entire time series. So this is going to be t goes from 1 to cap t, f w I t, given theta I phi. This is all inside of that. So for each rat, I sample this parameter, I plug it here, and then I get the whole time series of this. So every number of things that is sampled appears in the likelihood that's going to be one of its product terms.
Why is t start at 1, not 0?
Oh, t0. Just because I'm making a mistake. So then I'm going to product all of this over the I rats. So I product that whole thing up. Boom, 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 boom. That's the likelihood. The conjugate prior for this parameter is a gamma. The conjugate prior for theta I is a normal. We don't need a conjugate prior because we've got this conjugate relationship through the random effects. So that's acting as our prior, but it's a random effect distribution. Conjugate prior on theta naught is normal. And it turns out the conjugate prior on sigma inverse is called a Wishart distribution. I'm going to take you through that exercise next time. show you what a Wishart is very briefly. You'll write down what that distribution is. You'll figure out what all the full conditionals are. And here's a big hint. It's all in the review session. We worked all this out. So if you want some more help with that, getting through everything, just look at that review. I'll say a few more words next time. We'll jump into Jeffrey's. On Monday, I will do a yes, no, maybe section, and I'll advertise that to you on Friday. I'll record it as well. I'll tell you how it operates next time. That's it for now, you guys. So